Good evening, everyone. So today I will discuss about the advanced data GNSS data processing. Good evening, everyone. So today I will discuss about the Good evening, everyone. So today I will discuss about the advanced data GNSS data processing. So in this, you might have gone through the fundamental of GNSS as well as some processing techniques also by our reputed scientists. So in this particular lecture, I will focus some this fundamentals as well as some this, methodology which we use to get the millimeter accuracy to the GNSS data. And we know that GNSS data is very giving vital information for uh, your hazard, for mapping, for monitoring. So it has a ample application. So, and this when we talk about the millimeter, so why we need millimeter accuracy? Where we required such accuracy? So, because based on our objective, we have to select this data acquisition setup, then processing setup, then interpretation setup. So, it is always based on objective as well as based on the requirements. So we know that when we talk about the millimeter accuracy, we need mainly for the monitoring. And when something is moving in millimeter, centimeter, or in meter, so okay, submeter, then we need millimeter accuracy estimate through this GNSS data so that we can monitor those phenomena and in good accuracy as well as precision. Because sometimes we make it good accuracy, but we may not get the good precision. So when we want both in good this thing, then we have to have a very good antenna as well as receiver, because this is the fundamental requirement for this millimeter requirement achievement. So when our antenna is of choke ring antenna and element is very precise, it is like a DM element or Morglin element. Then receiver is like a very robust receiver, like your survey grade receiver, survey grade antenna. So then we can think of millimeter accuracy, because there are so many internal in this importance, and like your phase center variation in antenna. So if phase center variation is less than 1 millimeter in horizontal as well as vertical, then your capturing of this electromagnetic waves in particular frequency like L1, L2, L5 will be accurate. And if it is when it is hitting to the antenna and it is acquiring all those signal from different PRN, for instance, GPS like PRN1, PRN2, PRN3, PRN32. So it will be always be in sub-millimeter accuracy. So then, if this phase center is following this requirement, and it is happening in this accuracy, then it is going to the ultimately it is going to the receiver. Okay, so receiver, you must be knowing, receiver is producing the replica signal. So when your this GPS, for instance, GPS is transmitting the L1, L2, and L5 signal. Okay, so at the same time, your receiver is producing the replica signal, and this electromagnetic wave traveling through the velocity of light. But when it is propagating through this speed, it is getting hindrance through different media, ionosphere, troposphere. Okay, then there are many error budgets like orbit error, clock error, multipath error, your satellite drag, radiation pressure, so many error budgets associated with the data. So that's why, and this when this signal, when it is coming to the receiver, so in phase, this one-to-one correlation is not happening between the signal, your main signal, which is transmitting through the satellite, and the replica signal, which is basically creating at the receiver. And this is producing the phase difference. Phase difference. And this phase difference is having the time delay. Okay. So this time delay we have to eliminate from the signal. If we are able to eliminate in this millimeter scale, sorry, eliminate, then we can think of millimeter accuracy achievement. Okay. So how you can eliminate all those error budgets? So there are different models. Okay. So when I say model, so we need long period data to get the very accurate model of different error budgets. Okay. So some error are instantaneous. It is time dependent. Okay. And some require long period data. So this is how the model this required long period data as well as instantaneous data to get the to eliminate the error from the GNSS data. So in this image, so so this is the background of this your advanced GNSS data processing. So in this, I will be going through this flow only in the detail subsequent slide. So here you can see the global velocity estimate in millimeter accuracy, and these are basically in millimeter vectors. So here your movement is like 7 centimeter, 5 centimeter, 6 centimeter, 3 centimeter, okay, 2 centimeter. So these are the variation in the velocity vector, and you can see the azimuth. Azimuth also different for different vectors because all the plates are moving with in different direction in different magnitude. So that's why it is very important to monitor these plates because the moment of different moment of the plate give rise to different strain accumulation and subsequently the consequence will be in the form of earthquake, in the form of crustal deformation, in the form of your convection, convergent bound. It is mainly seen at the convergent boundary, divergent boundary, transform boundaries. You see the consequence of the plate movement. Okay. So, and this is very, very important, but it is not only limited to your crustal deformation or geodynamics. We are using it for land subsidence, landslide, mass movement. Okay. Then there are some more applications for this millimeter requirement. These are the GNSS satellites you can see and how it is developed, how they look like. You can see some of them are regional, some of them are local, global. So we know I no need to discuss all these things. So this is the specification of the GNSS, starting from the GPS to GLONASS, Galileo, Vedu, NAVIC, QZSS. So this NAVIC and QZSS, these are regional navigation systems. So, and their orbit constellation, your it is very, very different from the global. But Beidou is having some hybrid constellation. It is having some geostationary as well as geosynchronous, as well as LEO and MEO. Sorry, not LEO, MEO. And but GPS is having mainly MEO. GLONASS and Galileo is also having MEO orbit. It is having 20,000 plus, around 20,000 kilometer is the altitude. Okay, so I will not go for all this thing. You can get this material from me. So this is how we set up these GNSS stations. So on the left side, you can see the CORS, continuously operating reference station, and on the right side, you can see the campaign-based GNSS setup. So both are achieving the millimeter accuracy. Both the setup are achieving the millimeter accuracy, and both the setup can be used for monitoring, mapping, for many applications. Okay, but the difference between these two, one is continuous and one is your episodic. So this campaign mainly episodic. So if we don't have a budget, so we have to go for episodic measurements. And if you have a good budget, so we can go for the continuous measurement. So this is another setup. So, and this is how the antenna look like. This is the internal structure of the antenna. You can see how robust it is. And it is having the DM element. It is manufactured with the DM element. So very precise. And this is a very robust survey grade antenna. So, and this is how it is installed for campaign measurement. And this is another equipment for the campaign survey. Now I will move to the fundamental. So, and before proceeding to how we can process the GNSS data, I will briefly discuss the fundamental of GPS, our GNSS navigation. So we know that it is also called it is following the principle of this geodesy, and but it is space geodesy actually. So there are ground-based geodesy also, ground-based geodesy for the navigation measurement. So here we are discussing about the space-based geodesy for the navigation measurement. So we know that this GPS is having L1, L2, and L5 signal. So earlier we know that this GPS is having the code sources acquisition, then P code, then navigation message, basically exhibiting the broadcast, orbit, satellite clock or correction, ionospheric information, etc. And both are transmitting with L1 and L2 frequency. So these are the frequencies which is transmitting from the navigation satellite code signal, and this is the carrier signal. So carrier signal we use for the millimeter measurement, and code signal we use for the a priori measurement now at day. This is the fundamental equation for the code measurement as well as for this phase measurement, and it is following the principle of trilateration measurement. So here we are doing applying the trilateration methodology to compute the latitude, longitude, and height. And when I say latitude, longitude, and height, so it is with respect to your time meridian and your equator and ellipsoidal height of the Earth. And sometime we are but in our case in geodynamics we are using the geocentric coordinate also. So it is basically the data is from the center of the Earth. So that's why it is called geocentric. So this is your equation, fundamental equation. If we have a 4 unknown, so we need minimum 4 equation to solve the 4 unknown x, y, z, and t. Okay, so this is how we follow. But this is the velocity of light. This is the time difference, and this is the bias. So when we are able to solve this equation, we can think of millimeter accuracy. So when we have more number of satellites, we can constrain more our measurement and more our unknowns. So this is the Keplerian element. So Keplerian, there are basically 3 Kepler's law. We know that orbital ellipse, your law of equal areas, and law orbital with equal periods. So basically, this three Kepler's law we use to estimate these unknowns: semi major axis, eccentricity, inclination, longitude of ascending nodes, argument of perigee, and true anomaly. And with this parameter, we are able to give the information about the size and orbit shape of the orbit, orbital plane in the apparent system, and position in the plane. So, which is very, very important for this error budget estimate. So now, what is carrier phase observable? Okay, so we know that phase phase is nothing but it's the angle of rotation. So if we say if it is completing the 360-degree, okay, means one complete cycle. So when it is completing one complete cycle, it means it is completing one complete wave, 2 pi. Okay. So if we compare with the sinusoidal wave, so one cycle is 2 pi and is equivalent to your one complete circle. Okay. So and for example, you can see here. So this is the one complete cycle, and here is the complete. So for instance, if we want to see this point here on this circle, so it will be somewhere here. Okay, and you can see the formula. With this help of formula, we can estimate the amplitude. We can calculate the at this particular time what is the amplitude, what is the phase, all this information we can estimate. Okay, so this is the formula we use to get the to define to derive the sinusoidal variation of the GPS signal. And when we multiply this carrier wave signal with the this replica signal, so here you can see it is we are doing mixing with the your replica signal as well as the GPS carrier wave signal. So then we have to eliminate the your we have to eliminate the your frequency component, and this frequency basically we don't want because it is producing the more error. So we need to eliminate this. So when we are eliminating this, so it will be having we will be it will be leaving this component only. So we have when we want to eliminate this, we have to filter out. Okay. So after filtering, only this is possible. So once we filter, so this is the final equation, and it is also called phi bt. So this phi bt is nothing. It is equivalent to this equation, and I this beat frequency will be equivalent. This FB will be equivalent to the differentiation between the your phi b upon dt. Okay. So when we are using this previous equation here for the model of the model development, so when we can see here, so this is the your receiver observation, receiver time. Okay, phase as receiver, phase as satellite time, and this is the ambiguities, our error budget. So this is the your signal at time t at in a particular PRN satellite, and you can see you have to use the subscript and superscripts because there are so many satellites. So that's why we need to develop subscripts and superscripts. And this is for a particular satellite. And when we develop this, so this is the carrier phase observable. Okay. So you can see here, this is the time difference, this is the phase difference, and this is the ambiguity. Okay. So we need to expand this equation for a whole constellation. So this is how we can expand. So here we need to put subscript and superscript. Okay. So this subscript is for your receiver, and your superscript is for specific satellite. So this is the fundamental equation for model development. And when we use this fundamental equation for length estimate, length between the antenna and the receiver. Okay. So antenna and the satellite and the antenna, because we are able to this is our objective. So when we are able to estimate in almost true range, between the satellite and antenna. So then we can think of millimeter accuracy estimates through the fundamental equation. So this is the formula we use to calculate the length, okay, between the satellite and antenna. So after removing this ionosphere, troposphere, different error budget, then time delay, so then we can think of accurate length estimate. So how we can separate the time? So if you, because there is a time delay in receiver, there is a time delay in your satellite as also. Even though the satellite is using the atomic clock, and receiver is using the quartz clock. So there are tremendous difference because atomic clock is very very precise as compared to the quartz clock. Okay, but and also your this when signal is transmitting this electromagnetic wave, it is having the right-handed circularly polarized wave. Okay, so when it is coming and hitting to the antenna, your antenna is intended to receive the right-handed polarized wave. But sometimes what happens? Uh, if buildings are there, if trees are there, if canopies are there, if obstructions are there, so it is creating the multipath. So we need to remove the multipath from the this observation. So then what we have to do? You already have seen the chokering antenna. So this concentric cell helps us to eliminate the multipath. And what it does, it basically when it is coming and hitting to the concentric cells, it is reflecting back to the obstructions or your building or canopy. Then when it is and there it is converting, it is changing the polarization actually. So from right-handed, it is becoming the left-handed, and when it is coming again, and it is coming to the face center zone, and it is not able to detect because our this antenna is intended to receive this right-handed polarization wave only. So this is how we are eliminating some extent the multipath, and rest we are modeling it and we are eliminating from the error budget our data. And the signal differentiating we are using to eliminate the clock bias from the your satellite, and double differentiating we are using to eliminate the clock bias from the receiver. So this is the architecture of the signal differentiating and double differentiating. In this case, single satellite we are using, and double station we are using ground station. But in double differentiating, we are using the two satellites as well as two ground stations. And this is the modeled and this real-time estimates of the this PRN, our frequency information. So you can see how accurate it is. Okay, so there are very, very, very less deviation. Okay, so this is provided by your MIT USA, this information. And this is the observable in data processing. So you can see that we have to do the linear combination. We have to make the linear combination. We have to do the partial derivation also. So this is how we are doing. So these two equations basically intended to eliminate this ionosphere free phase combination as well as ionosphere free range combination. So these two we are eliminating from the observation through these equations. And this is not a one, this we are iterating actually. We are iterating after making the my matrix, we are iterating this through the different softwares like Gamut, Bernice, Gypsy. There are different platforms, and all platform following this principle, same methodology, and they are eliminating the this error. And double differencing basically removes the clock fluctuation, and linear combination removes all the ionosphere, which is ionospheric error present in the data. Okay, then we are also making geometry field combination through these equations, and then we are using the MW and WN, and this we are using to eliminate the phase hour pseudo range combination that removes the geometry and ionosphere dominated by pseudo range noise. So this is how we are following and moving through the steps to process the GNSS data. And what happens? Some of them this error budget, we are not able to get the very accurate model. So like there are different models like Earth gravity field, attraction of sun and moon and sun on the satellites, then irregular rotation of the Earth, then lunisolar solid Earth tides, then neutral atmosphere, then ionosphere. So this we are able to model accurately through the long period data. So this defines the motion of the satellites, motion to the of the Earth, propagation of these are the this is how it is affecting the data. So, but in this, which is mentioned through different color, we are not able to get the very accurate model like solar radiation pressure, very complex phenomena, loading due to oceans, atmosphere, sun, surface, water, and ice, very complex phenomena. So it is we are, and also data is very limited for these observations or for this physical phenomena. Then variation in the phase center of the ground and satellite antenna. So sometime due to human error and sometimes poor quality of antenna. So making difficult to model this error budgets. So that's why when we are going for this millimeter accurate measurement, uh, we have to just follow very accurate this procedure so that we can have the very accurate model. Okay, and when we are, as I told you, we have to process in different open source platform like Gypsy, Gamut. But this Bernice is not open source. It is, but you have to take the license for this if you want to purchase. And then and when you are going to process your data, you need to set up the your this file. Okay, folders setup you have to do. So you have to keep your Linux data, your error budget, your folder you have to make, then table information you have to make, like your satellite information, your antenna information, receiver information. All this information is required during the processing. Okay, apart from your model information. So this is how we need, and then we need to estimate the parameter. So these are the steps to estimate the parameter by this following procedure. And once we do this, we get the loosely constant solution. So once we get the loosely constant solution, then we go for the post processing. Okay, for the time series estimation as well as the velocity estimation. And for that, we use the Kalman filter, and we use some more procedure to get the continuous time series from the loosely constant solution. And we need to set up the reference system also, because as I told you, there are different reference system like ITRF is there, WGS 84 is there, then geocentric datum is there, ellipsoidal model of the Earth is there. So this reference system is there, and this reference system is not static; it is kinematic. So many models is required to continuous update this reference system. Okay, so I will little bit give the overview of this reference system also. So these are the some uh, this this these are the some effects which limits the GNSS accuracy. Okay, so and you can see here the different error range in for different error source. Okay, so maximum error is producing through ionospheric delay only. Okay, but you cannot ignore the error budget. Okay, so once you apply all the error budget, you can have the millimeter accuracy from your data. So I will very quickly describe the limits of GNSS accuracy because I'm running by time. So here you can see this propagation, how signal propagation is getting affected. So you can see here, this is the setup of the campaign, and this is very close to your building. So now you can see here, this is the obstruction. Okay, so if the satellites are here, it will not get tracked here. Okay, because this is creating the obstruction. So it will only track in this range. The satellite which is in this range It is only sort of track those satellites. And then when it is tracking all the satellites, so due to the presence of this building, it will track the multipath as well as apart from the direct signal. So direct signal is also coming, but signal is also reflecting from the ground as well as from the building. Okay, so it is also getting tracked, but more contribution is from building than from the this ground signal. So now we need to take care of this setup of the campaign station. If we are very, if we have, if we are very means we cannot ignore this location, and we have to set up the campaign station here only for some specific objective. So then what we have to do, we have to set up here the chokering antenna, what I have shown you. So if you are setting up the chokering antenna here, so then it will take care this reflected wave, and it will some extent eliminate all those signal, reflected signal from the building. Okay, and I already explained you the concept how it will eliminate the this reflected signal coming from the building. Okay, then it will mostly track the direct signal which is coming from this range, and then it will you can process the data and you can generate good positioning of this location. So this is the some example of this antenna at a different elevation angle. You can see here, this is the antenna height 0.15, this is the antenna height at 0.6 meter, and this is 1 meter height. So you can see the variation. This is the linear combination multipath. Okay, so you can see for these three different antenna height, and this is giving information from 0 degree elevation angle to 90-degree elevation angle. So 0 degree elevation angle is the horizon. Horizon is the 0 degree elevation. And when we are, it is when it is right on the antenna. When it is right on the, when it is right on means it is top of the antenna, it is called 90-degree elevation angle. Okay. So this is how we define the elevation angle. And what is azimuth angle? So it is basically the starting from the north, okay, and it is following the clockwise direction, and 0 to 90, 90 to 80, then 80 to 270, and 270 to 360. So complete 360-degree is the your azimuth angle. So this elevation angle and azimuth angle we use to define the position, to determine the position of the satellite in space. Okay? So this is how we take the position of the satellite in space. So this is the atmospheric change. So this is, you can see the water vapor contribution here for this. You can see how it is look like. And this is the, as I told you, this is the horizon, and this is the 90-degree, and this is the antenna. So we can see how it is depending. Okay, so it is, and we know that this your water vapor basically we get in the neutral layer, and neutral layer is nothing but it's a troposphere layer. Okay, so this is way, and some temperature and pressure we are able to model. Okay, because it has some linearity in their variation, but this water vapor is non-linear because it's very complex phenomena, and it is very sometimes it is very regional phenomena also. So it makes us difficult to model this water vapor in accurate manner. Okay, so that's why sometimes we are not able to completely eliminate error budget due to the vapor contribution, and you can see clearly here the contributions. Okay, and you can see here the multipath. So this is the scale, and this red curve is the basically the variation. You can see the path track, actually the track, satellite track, and along this track how much multipath has been created. You can see that. Okay, so this yellow, green, so this is the positive and negative residual. Okay, purely of a visible effect. So you can see that, and this is the scale, and through this scale you can compare that how much positive and how much negative residual is present in the signal due to this multipath and water vapor effect for a different time period. This is 12 to 18. This is 18 to 20 UT. Okay, universal time. Then this is 20 to 24 universal time. So for this three different period, you can see how the multipath and water vapor effect is contributed globally. So, and another is unmodeled motion of the station, like instability, loading of the crust, okay, by atmosphere, ocean, and surface water. So, and this monument instability is completely the anthropogenic or completely the human error. So, and the other effect is can be your this natural phenomena. So, natural phenomena can be your this discontinue to do the environmental changes. Okay, equipment or environmental changes. Discontinuities due to the earthquake, non-linear motion due to the earthquake, non-linear motion due to the transient event like volcanic inflation episode, landslide, a deep-seated landslide, your convection current, volcanic, the land subsidence, okay, mining activity. So many natural phenomena and anthropogenic phenomena is taking place, and which can create a irregular perturbation in the signal. So these are some examples. You can see the non-linear motion, and you can see here this is due to the hydrology. So this is due to the hydrology. You can see the sinusoidal variation in the signal, in the height mainly. So this the so how the contraction and expansion take place during your different during the whole cycle of the your hydrologic cycle. So you can see the spring, summer, fall, winter. So this is the complete cycle, and during this complete cycle, your land is going through the elastic deformation. Okay, so then it is elastic deformation is taking place. Then again, compensation is again taking place. Means it is coming to the original place. So when it is getting contracted, then when it is coming again to the natural position, so this contraction and expansion is taking place. Okay. So due to this, we get the negative and positive now in the mainly in the vertical component. So this is the annual component of vertical loading. You can see that how globally it is taking place all around the world. So this is the vector of the vertical loading, and you can see the direction also. Direction also it is different. It is not same in all the plates. So the last is your second last is your unmodeled motion of the satellites. So as I told you, the this non-gravitational acceleration due to the solar and Earth radiation, unbalanced thrust, outgassing, non-spherical harmonics, spherical antenna pattern. Okay. Then modeling of this effect has improved, but the global analysis is a problem. So this also creates a difficult to eliminate all the error from the data. And last is the reference frame. If the frame is not accurate enough, because when you are going to make the reference frame, so there are so many inputs required. Okay, so for example, your accurate plate information, accurate velocity information, then your polar wandering, your this rotation of the Earth. So all this required in accurate manner. Then there are different platform, different data which providing this critical information like VLVI, SLR, GPS. All these are providing information. So when these are very accurate, so then we are able to model it, and then we can have very accurate data in different like WGS 84, ITRF, International Terrestrial Reference Frame, then geocentric, ellipsoidal model of the Earth. Okay, we are able to model the very accurate geoid through GRACE data. You know, GRACE satellite, which is providing the gravity information globally. So once we get all this thing done, then what we have to do? So this is the flow chart. So this is the antenna. This is the some this instrument. Okay, there are some more instrument nowadays. So these are the some this OEM providing the this antenna receiver, and then they are this is the raw data format. Okay, and then we need it's a very single format like RINEX receiver independent exchange format we need. So once we have this text this ASCII format which is the standard and it can be used in any of the platform. So once we get this, so then we can use this so this is the raw data format, RINEX format. So here we can see the C, L1, L2, P1, P2, S1, S2. So you can see how this is acquiring at 15-second interval, 1 second interval, sampling interval. You can see this is the header information. Okay. So this is how the data look like, the raw data look like, and for different PRN. So once we get this, so this is the so here we keep the data and we keep the orbit file, navigation file, table information. We need to update the table for our ground station, for IGS station. So once we complete all these things, so then we have to go for the processing. Okay. So then we use this gamut platform. And once we run the this gamut process, and when we do the gamut processing on through this on our data, so then we get the ASCII file. That is also called H file, and it is keeping having the loosely constant solution. And we use the GlobeK platform to process this loosely constant solution through the Kalman filter and other method to get the time series and velocity. Okay, and here we are using the Galred and GlobeK to calculate the time series and velocity of the station. And this is the phase residual plot. So this is how we can see how it is getting constrained for a different elevation angle. What is getting constant? So we can see that. So if we, you can the quiz, you can have it. So there are total basically 8 questions. So you can go through this quiz and you can it's basically check yourself that how much you understood from the lecture, and if you have further question you can come later on and you can discuss with me. Now I will briefly quickly discuss about the case study. I have only 15 minutes left. So these are the GNSS station, and it is installed by Survey of India in all around the Indian territory. You can see that, and it is almost 1,000 plus stations. So you can see it is not only limited to your this boundary only, but it is they are set up completed the setup in Lakshadweep, Andaman Nicobar. So all this complete belt is equipped now with this continuously operating reference station, and this data is 24 into 7 available at their server, and you can always go there and ask for the data and for your objective accomplishment. Okay. So once you get this data processing done in millimeter accuracy, so you can see you can do many applications. So like this is the crustal deformation study, for instance. So you can see this is with respect to the your erosion plate. This motion is indicating with respect to the fixing the erosion plate, and here you can see the very high velocity, and here here the velocity is decreasing. Here you can see the velocity is decreasing. Okay, and you can also see the direction. Direction is clockwise. So this erosion plate is moving in clockwise direction, and our Indian plate is moving anti-clockwise direction. So these two phenomena is already proven, and by this GPS only, that how our plate kinematics is all globally. So our Indian plate is having anti-clockwise motion, and it is all and it is quantified as 0.5 degree per million year. Okay, and it is given by, this estimate is given by many authors. And from India, Professor Dr. Sridevi Jade Madam has given this estimate, and you can go and read this research. And you can do the hazard also through this GPS. So this hazard is doing by many global as well as our national researcher. Okay, so you can see this is some of the research done by your Wilhelm et al. So this is for whole Himalayan stretch, the plate where the locked segment is there. So you can see the black patches is showing the locked segment, and this is the estimates, okay, which is giving the information about the how much sleep potential is there, how much sleep can be released in near future, and through this seismic moment and moment magnitude. Okay, and this is for Kumail Garhwal information. So here two earthquake occurred in the instrumental era. So 1991 and 1999. So 6.3 and 6.7 has been occurred, and the big earthquake occurred in 1803. So if we compare with respect to the 1803, these two earthquake has compensated, has accommodated the energy in these two, in the form of these two earthquake, but huge energy is still present along the plate, along the fault plane, and this and the continuous strain accumulation is going on. So it is not that it is not sustainable. It is not prone to occurrences of the big earthquake. It is prone to occurrences of the big earthquake near future. So that's why we need to have more study through this GPS, your satellite, SAR based, then ground based, then precursor study. This all these studies need to be updated, need to be done in real time, near real time, to get the this hazard information. Okay, we need to update this hazard information, and we need to propagate this information to the society, so that we need to create the preparedness. We need to create the awareness. Okay, about the future occurrences of this multi-hazard phenomenon. So this is our study, and we have set up basically ISRO has set up basically around 30, 35 stations, and three and more centers mainly working on this GPS, SAG, NRSC, IRS. So IRS has set up 14 GNSS stations, NRSC has set up 7, 8 stations, SAG also set up in Northeast, mainly Northeast region. Okay, so 200 for this coastal reformation study. So our study also given has produced very significant information, and it has provided very good science about the ongoing coastal formation in this Uttarakhand and neighboring region. So you can see here we got the information that how this HFT, MBT, and your MCT region, how the strain is accumulating, how much shear strain is there, in which direction your shear strain is more and high, and also compression, extensional strain we have estimated through this GPS data. So you can see here that how your compressional and extensional strain is increasing, and what is the direction of the compression and extension. Okay, so this all we have done through the GPS data. And after getting all this information, we have modeled this data also. Okay, so after modeling, we got the information that how much how much the segment of the plate is locked, and how much energy it has been accumulated, how much seismic movement is present all along the fault plane. Okay, then what is the fault lane, what is the fault width, what is the locking depth. So all this we have been estimated through this GPS data after modeling the uh, after doing the modeling in the through the Okada green function in the elastic half space. This is the another case study giving the information about the how the hydrology is present, how the hydrology affecting the your strain accumulation of the strain because of the perturbation of the plate motion. So you can see here this three season how the variation of this mass contribution affecting the movement of the plate, and also you can see here the this is the correlation between the your basically the displacement and the your the displacement and the loading. So you can see the east component, the loading effect is very less, but north component, the loading effect is uh, some prominent and as compared to the east component. And vertical component, the loading impact is very, very high. So as I told you, it is mainly influenced due to your hydrological contribution. So because this north component, more influence is due to the crustal deformation only, means due to the convergence of the Indian plate and it is subducting into the Eurasian plate. So more contribution is there, but we cannot neglect the contribution from the hydrology also. So it is also affecting the in regional scale. We can see in the regional scale it is also getting affected, but east component very little are getting affected. I think the east component it mainly record the movement in the if there is a strike component. Okay, so strike component is there. So then it is getting more contributed in the east-west direction. But this north south component mainly get influenced by the your convergence as well as the hydrology. But the vertical component is mainly get influenced by the vertical contribution. Mainly, sorry, due to the hydrological contribution. So this horizontal, your convergence is having less contribution. So we know that this Himalaya is rising. So of course, your plate convergence is contributing to rise the Himalaya, and it is mainly happening in the lesser Himalaya and the higher Himalaya. But this your Indo-Gangetic plain and this IGP and your Shiva lakes having less influence of having less influence in the vertical component, and this rising component is very, very less. So, and this GPS is also useful in your vertical component, and people are now using this for precursor study. Okay, so this is a emerging area in your hazard study. So, because in seismogenic phenomena, because before the occurrences of the earthquake, there is a seismogenic phenomena along the fault plane. So, what happens? Rock get overstress. So, due to this thermal changes and over more thermal activity all along the fault plane, it break the bonding in the pyroxy and it mainly happens in the igneous rocks. So, these positive holes get free from the rock and it comes to the surface due to the potential difference, and again it goes into the ionosphere due to the subsequent potential difference, and it get accumulated at the lower surface of the ionosphere. And then what happens, it get your diffusion take place, and depletion of the your electron content take place in the ionosphere. And when this your GPS signal, our GNSS signal is transmitting, so we are able to observe these changes in the your depletion in the total electron content, okay, in the ionosphere. So this is not happening. This is not only happening due to the seismic activity, but it also happens due to the solar contribution, due to the geomatic contributions, and where it has a, where solar ionosphere layer has a tendency to deplete the total electron content as well as enhance the total electron contents in their zone, in the ionospheric zone. Okay, so that's why we need to carefully study the this total electron content variation in the particular zone, and we need to understand whether this is due to solar activity, geomagnetic activity, or either it is due to the seismogenic activity. So this is the future demand to need to model the data, to need to decompose the data, okay, to separate the observations from the solar, geometric, and the seismogenic activity to it to constant it and to use it for the hazard study, because because if the solar activity and geometric activity parallelly occurring during the seismic activity, so it creates the limitations, and then we cannot use this GPS, our tech study, for our earthquake hazard study. So that's why we need more this more advanced study in this and model development, so that we can use it for earthquake study also. So these are some of the this case study where we have successfully uh, achieved successfully detected the tech anomaly before the occurrences of this Mirpur earthquake of 6.6 magnitude, moment magnitude. And these four stations and all these four stations located at different located especially different distance from the earthquake, and having different tech also. We can see at particular time they are having different tech values. Okay, so this gives information that how the tech variation take place with respect to the distance from the epicenter, upcoming epicenter, and this is the anomaly. And if we are able to model it very accurately, so then we can get the approximate epicenter also. So this approximate epicenter can be forecasted, and it will be a great help to the society for the upcoming mega thrust earthquake, because this 4 magnitude, 5 magnitude, and some extent 6 magnitude also create less hazard, but more than 6 create tremendous hazard, and big area, big society uh, could create a cause, and could basically face the more devastation. So that's why if we can get this some extent this epicenter information, so then we can have the very good preparedness about the upcoming earthquake. This is the spatial calculation of the tech through the global data. It is also called GIM data, globally ionospheric map data. And here also you can see this, this model, this data has detected the anomaly before the occurrences of this earthquake, because your this anomaly has been detected on 16th September, and earthquake has occurred on 24th September. So you can see there is a good time of 8 days. So this 8 days is more than enough to do the preparedness and to basically alert the society. But as I told you, this data require more and more this study, because it is this tech is not only contributing, this tech variation is not only contributing by the seismic activity, but it is also contributing by the your solar and geometric activity, and some more physical phenomena is taking place. So we need to decompose it, then we can constrain it, and then we can use it for the earthquake hazard study. So how this is some more example of this land deformation. So you can see the land deformation took place in the Josimat region. So you can see the non-linear motion, because this is not expected from the CORS. If you see the CORS displacement time series, you will always see the linear motion. Okay, linear motion. But if you are getting this non-linear motion, so it is not due to the tectonic activity at all. It will be always be due to the local phenomena. Our landslide, deep-seated landslide, land subsidence, mining activity, or some other activity. So you can clearly see here that this non-linear motion, and we already have seen this ground deformation over there. Okay, and this is the campaign data. The campaign data we have installed actually. We are monitoring since 2015. So it has also been recorded this land deformation, and it is not giving whether it is linear or non-linear, but we have confirmed by the velocity estimate. So here the velocity is more. So this velocity never it cannot be due to the tectonic activity, and that's why this is due to the deep-seated landslide movement activity only. Okay, so these are some references which you can go through it for more detailed study, because in 1 hour it is impossible to cover all the aspects. So I hope I have given my best to make you understand the advanced GNSS data processing. And if you have more doubts, more queries, you can always reach me through email ID. Okay. Okay. So you can also reach to the EduSet and to get more detailed information. And thank you very much. Thank you for your patience.